In the video we can see our system, a mass that swings oscillating on a spring. The origin of the axis is the fixed attachment point and the positive orientation of the y-axis is upward. The calibration length is 0.7 meter. The time between video frame is 0.095 seconds. I saved the position data in the file written here. In Italy we use the comma instead of the point for a number, and this is a problem for me. And this is the computational model. The ball position is from tracker 0.105 minus 0.756 and 0. The velocity, the initial velocity is 0, because I chose the position in which the mass is at the highest point before falling. The ball's mass is 0.402 kilogram. I have underlined the difference between our system and the system analyzed in the video lectures in one dimension. The most important thing is that L0, now in two dimension, is a vector. We can see here that L0 in one dimension is a scalar. Its direction does not change. Instead, in two dimension, L0 has the same direction of L. And so we can write L0 in this way. And the stretch S is also a vector. In the calculation loop, the time from tracker is 8.072. In the fourth spring appears S, that is a vector. We don't need L hat. We have to update also L0. For the energy, the only change is in the expression of the spring potential energy, in which S is substituted with the magnitude of S. And now we can run the program and compare the model predictions with the observed motion. In blue we have the model, and in red the real motion. If we change here and here, we can plot the energy changes computed in the model. Delta K is in blue, delta U sub S in red, delta U sub G in green, and their sum in yellow. The graph shows that the sum of the changes in each type of energy is equal to 0, so the energy principle is satisfied. We can note that the initial ball position is A, after one swing to the left is B, and after another to the right is C. The point C does not correspond to the point A. In fact, C is higher than A. If we consider a simple pendulum, after a full swing, C is in the same position of A, and K and U have the same maximum and minimum at the same time. For our model, K and U have maximum and minimum at different time. It seems that delta E is equal to 0, but if we zoom, some oscillations appear. I think this is due to the use of delta V over delta t instead of the derivative of V respect to the time. In fact, If delta is smaller, the oscillation's amplitude decreases. From tracker, the oscillation period for the x position is 1.6 seconds. For y position is 1.48 seconds. It means that the trajectory of the ball changes at each swing. I have plotted the magnitude of L, the y component and the x component of L versus time. We can notice that the period of t magnitude of L is equal to the period of Ly and represents the period of the spring's oscillation. Tlx x is the period of the pendulum swing, and these two periods are different. By trial and error, I found the value of mass for which t pendulum is twice t spring. The computational model for this new mass is here, and if we run the program, we see that the trajectory is the same for each swing.